Hey guys, welcome to Deep Learning Explainer. And today's topic is very exciting. It's about distilling task specific knowledge from BERT into simple neural networks. So basically, it's a paper they saying that you can have a larger neural network, which we make it as a teacher and teach analogy to a smaller neural network, which can run faster in the inference time and also have a smaller model size. So how to transfer this kind of knowledge, we call the distilling, or you can call it distillation. So yeah, and why is it so special about this paper? This paper is actually very interesting for several reasons. The first reason is this is task-specific distillation. It's more efficient than the general distillation. Basically, there's several works on the language model distillation. So how it works is like it has large neural network and teach the smaller neural network over the corpus, the huge corpus like Wikipedia, Google Books, which takes a lot of time to do the distillation. And this one is like we just do the distillation over our specific task, so it's much more efficient. And also there are actually very few distillation papers for NLP. It's actually an emerging area, but still not quite well researched yet. So this is one of the very few papers talking about that. And there are a lot of interesting experiments in this paper. We will also go over that. And more importantly, it also provides us the inference time comparison. Because why we care about distillation, a lot of time is because we want to have the faster inference time. And this paper actually shows us how you can have a better inference time. And if you are now in the academia area, if you are in the industry, then you probably care inference time a lot, because if you have long inference time, you hardly to make your model real time, or you need to spend a lot of money to get a machine GPUs just to make the model run. Okay, so before we dive in, I want to ask you a favor. If you would like to receive more deep learning videos that explain a lot of different deep learning papers like this, don't forget to subscribe, because your subscription is really providing a lot of motivation for me to make more videos like this, because preparing these kind of videos really takes a long time. I need to read the papers and make slides and organize how I should present. So yes, thank you if you subscribe. Okay, so without further ado, let's dive in. So this paper, I already read the name, basically about this distillation. And this paper is from the University of Waterloo in Canada. So very interesting paper, I would say. And first of all, I would like to introduce why do we need to do distillation. Why? And there are several reasons. I already mentioned a few of them. And the first reason is actually NLP models are getting more and more heavy. As you may know, there's a lot of super large language models, pre-trained language models. For example, BERT, XLNET, Roberta, T5. Those language models are actually really big, and they are actually good for boosting those kind of research data set. But in the real world, if you really want to run those models, you will definitely have hard time, because you have a limited budget. You don't have unlimited computational resources to just run those models. So people are thinking, how can we compress those models? There are definitely a lot of lines doing model compression, quantization, and distillation is another solution for that. And this paper actually did a very thorough experiments and some other things for that to address this problem. And another reason is because definitely it's also related to computational power, because you have shallow models, smaller model, you have better inference time. That's very, very important in practice, in the real world applications. And the last one is also your model will have shallow model will have a smaller model size, which make you able to deploy those models to your mobile phones. And because a lot of people are using mobile devices, and we are in the world of like mobile first, so definitely you will be good to put those kind of models to those edge devices. So that's what distillation can provide us. And so for the knowledge distillations, basically means you kind of distill the knowledge from another model, from a larger model, and put it in simple words. Basically, you will have one neural network, which is really good, really good performance neural network. We call it teacher, and we have another shallower neural network. We call students. You can build a kind of these two different networks in very different architecture, no problem, and students still will be able to learn. But the problem is really the problem. If we just lay the most naive solution is we just let the teacher to predict our data, to run through our data and make a prediction. For example, if we want to do a sentence classification task or image classification, for example, image classification, we let the teacher to see our data one by one, maybe this picture, and teacher will predict if it is dog, if it is cat. Then the student also try to use teacher's prediction as answer and try to learn from the answer. We treat it as just a simple classification problem. But the problem really is here. There are actually a lot of dark knowledge in the neural network prediction, because usually the neural network predictions is a distribution of the probabilities over the classes, your output classes. And what I mean by this is actually, if we are given this picture, which is apparently a duck, and if the neural network predict this as a cat or lion, things like that, you won't say that it's too wrong. It's not that wrong, as it predicts this as a computer or skyscraper or some other things like sports car. It's very off. So the neural network, actually, when you do the prediction, it's like probability, and you probably will give the dog class the most probability, like 90%, and like cat 5%, lion 5%, and the computer maybe it's 0%. And we call these kind of things the dark knowledge. And if we just let the student network to learn this in a purely classification way, we will only have the label which called dark is probability 1, and the rest of classes or just have probability 0. And the student network will not be able to learn this kind of dark knowledge. Another example, let's say we are doing language modeling, which is to predict the next word. Oh, okay. So maybe I give you an example. I have maybe this answer is I have a very expensive computer. So I mask the word computer. I have a very expensive blah blah blah, and you need to predict the next word. Answer is computer. So if the neural network predict this word as I have a very expensive apple, then you won't say it's totally wrong because it's like grammatically correct. But if the neural network predict this, I have a very expensive eye. The word it predict the word eye, it's completely wrong. And this is kind of things that we don't want neural network to kind of learn. But if we just do it in a one hard encoding way, the hard classification problem, the neural network will not really pick up this kind of a knowledge to know, okay, I know dog is the most probable class, but the cat is also quite likely compared to rest of the classes. Neural network won't be able to learn if we just treat it as a hard classification problem. But if we make it like a soft classification problem, we can easily address this problem. Okay, so put it in simple words, we want a model to learn this kind of dark knowledge. But how? This paper actually gives us some approaches. The first approach it did was we predict logics. We do some logics regression instead of just do the hard classification, which I already mentioned. And another one is because this kind of a distillation teacher actually needs quite a lot of data to teach your student neural network. Then how can we generate more data? In this paper, it proposed some data augmentation way to let the teacher to have more material to teach student. But I will not say their way of data augmentation is novel. Basically, I would say it's very basic data augmentation in NLP. But it's just argue that you need more data to let neural network to learn more efficiently. Okay, so their model architecture is basically their teacher neural network is a fine-tuned BERT neural network. Basically, they are doing this for some specific task. So they have the BERT as an encoder and plus one prediction layer and to do their given task. For example, sentence classification, sentence alignment, that kind of thing. So they fine-tune the BERT model over those kind of downstream tasks. And their student is just very basic bidirectional LSTM. This is their model architecture, teacher and student. So this is the like what they did for the sentence classification. This is their student neural network. So basically, first they have a word embedding layer, and they use word to vect as a pre-trained weight. And after that, you will have bidirectional LSTM. Then they do the concatenation from the first time step and the last time step, and they fit into another feedforward neural network and have the I think it's a relook activation function. And in the end, they have another softmax layer, and after that, you have sentence predict classification result. And this is like for sentence alignment kind of task. And it's basically very similar. They kind of calculate the representation for two different sentences, and they use bidirectional LSTM and concatenate the first and the last time steps. After that, another feedforward neural network with relook activation, and in the end, the binary classification that basically is like the softmax layer in the end. So those are very basic ways to do NLP in the past 3 years, 4 years, I think. So here comes the important point. Distillation objective. Distillation objective. So basically, the objective is they want to let the model be able to learn those kind of dark knowledge. And how they do that is basically treat this as a soft classification problem. So this is when we do a standard neural network, we will have a softmax layer, and after that we will have probability over every classes we have, like the previous example: cat, dog, computer, lions. So this is our representation, is our weight. This is our hidden representation, and this is our weight, feedforward neural network weight, our softmax layer weight. Then after you do the metric operation, then you will have the value, and we use this value. We put this value to the explanation, this function, And this function is we call softmax function, and it will give you a probability of each given classes. And we call this H with this W matrix, the operation, the result, then we call logits. And what we actually want is we want the model to learn logic instead of the end prediction, one hot encoded prediction from the teacher. So this is just, I want to tell you what do they mean by logic here is this value in the softmax function. So how do we make the model, the student to really learn these things? Basically, we can treat these things as mean square error loss. So how do we really learn? Basically, we have the student's logic. We have teacher bigger neural networks logics. Then we just subtract these two values and do some square error normalization, this kind of stuff. So if their logics are really far away from each other, then they will got a lot of penalty. And we want this kind of students' logics and teachers' logic as close as possible. And why doing this is good? Because we can, other interpretation is like we can have more learning knowledge, learning signals. Because in the hard classification problem, we only said, oh, this is a cat, and that's all. But if we just learn from logics from a teacher, we actually can see, whoa, this is cat, or this is dog, but it also looks like cat. It also looks like lion a little bit, and it doesn't look like computer. So model can learn from that just by this formula. We do the logics, mean square error loss, and that's all. And basically in this paper, they also try to use other kind of loss functions, but they find out mean square error loss function works the best, slightly better than others. Okay, so there are also another way to do this, because actually if we are doing this for a dance specific task, means we already have labels. Right? So basically when we do a task specific distillation, means we already have label for those given tasks. And it will also be great if we can lay the model to learn from the answers. Because if we only use this kind of mean square error function to lay the student to learn those kind of logics from the teacher, that's good, but it's not perfect, because teachers probably will also make a lot of wrong predictions. It's not perfect. And what we actually have is that we have 100% correct answers. And if we let the student to learn something from 100% correct answers, that's actually even better. So this formula is like they combine the traditional cross entropy loss function and the logic, like mean square error loss function. So this formula is just the distillation loss function that we discussed in this slide, and this is just the hard classification problem, and we have the loss here, and you have a hyperparameter here, basically is alpha. If you want the model to learn more from the teacher stock knowledge, then you kind of decrease the alpha. But if you want a model to learn more from the standard label, then you kind of increase alpha. So this is the formula, how it works. And also when they do the data augmentation, because those augmented data actually doesn't have labels, so when they run this kind of a teacher-student distillation over the augmented data, the label here is basically become one hard label. They teacher teacher network predict. It's not the answer, but it's like predict by teachers. So they kind of do this kind of adaptation for different kind of data. And here we have data augmentation for distillation, because the teachers need more data to teach students. If we just use those kind of label data, annotated data is not sufficient. So what they do was to kind of augment the data a little bit, and they use the teacher to generate the pseudo labels here. Then we just treat those pseudo labels as answer, and run the course entropy loss function. So the student can learn the dark knowledge and kind of one hard labels at the same time. So the first way is masking. So they randomly mask the word in a sentence, and like for example, I love the comedy. They just randomly mask the word love, become I mask blah 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 the comedy. And because this sentence is augmented, basically it has no label. Let's say if we want to do the sentiment classification, then because it's no label, so the teacher will just predict if this is like what kind of sentences, what's its sentiment. Then the student will just need to learn the logics from the teacher. And yes, that's a kind of an interesting way of generating data, because we don't actually need to have labels. So that's kind of provide us more possibilities of augmenting our data, because in some NLP data augmentation, we need to still kind of reserve the label of the data. But in this case, we don't have to. We just need to let the student to learn as much as possible from the teacher. Okay, so second way is POS-guided word replacement. So basically, it's like it replaces. They will just run the POS tagging first, then see what's the POS of this word, and replace another word with that, given very similar, basically the same POS. So both of these words, WH words, have the same POS tag. I think it's like WH words or interrogative, this kind of stuff. They replace that with what with how. So the meanings doesn't change that much, but even it changes a lot, I would say it's still okay, because we don't really need to have label, right? We just need a teacher to predict something, then later the student neural network to learn that. Okay, so another one is n-gram sampling. So basically, they just randomly sample the n-gram from the example, and the n can be 1 to 5. So basically, the effective things they're actually doing is randomly drop off the other words in the example. For example, I have a pen is our example, and in this case, our n-gram is like 2 is bigram. Then we just randomly choose bigram here, a pen. Then we drop off like the first 2 words, then become the sentence, a pen. So I'm not sure why they do this, but it's still okay. Just like I say, we don't have to have labels. So just we can do basically whatever we want. Basically, as long as the sentence makes sense, still makes sense, then the teacher will predict something and will generate logic. Then student can learn that. And that's all. That's all we want. That's the power of. That's why distillation is kind of super powerful. It's kind of a semi-supervised learning for student neural network. Okay, so here are their hyperparameters. Their bidirectional LSTM has 150 hidden size or 300 hidden size, and the ReLU activation layers basically is feasible neural network with ReLU activation function, and they have 200 dimension and 400, and their word embedding is just fixed 300 dimensional word vectors they got from Google. I think, yeah, that's a very, very typical way of doing LSTMs. Alright, so here we have a very exciting experiment time. We can see what kind of experiments they do and what's the result. And the first results are interesting. This is their distilled by directional LSTM, and to make some comparison, they also implement their own bidirectional LSTM to make sure their bidirectional LSTM is just working. And this is bidirectional LSTM they implement by other people. They publish in other papers. So this is our baseline model. So large BERT and the BERT base and the GPT. The BERT ELMo here actually is just ELMo, but because when the BERT paper was published, they want to compare how the BERT do compared to ELMo, so they also implemented another ELMo. So it's another ELMo here, basically ELMo model, and this glue ELMo is basically another when other people publish paper, and they also implement the ELMo model here. If you want to know more details, you just look at the paper. They have all the details. It's a little bit complicated, and so here we go. You can see the distilled by directional LSTM. Basically, they do a distillation. They learn from the large BERT, and their performance is very comparable to ELMo model, even like surpass ELMo in very different tasks. And you can see in these tasks, bidirectional very simple bidirectional LSTM after distilled is actually better than ELMo, which is very, very impressive. And here's also a very interesting phenomenon. The same model architecture here bidirectional LSTM, but without learning from the large BERT, it basically have very, very different performance. It's like 4% accuracy difference. So if we look at this task, QQP, and they actually also very, very significantly outperform the plain bidirectional LSTM. So what we can learn from this is like LSTM actually has so much potential. We just didn't really unlock it yet. And if we feed in more data, more knowledge to learn, it actually can become very, very smart, very expressive. Even can outperform more complex model ELMo. Yeah, if you understand ELMo model, it's basically very, I would say, quite sophisticated model compared to just their bidirectional LSTM here. And I think for all the tasks, most of tasks is very competitive with ELMo model, even better or competitive. But as for if you want to compare to its teacher BERT, you basically it's not really comparable. Still like 1 tier or 2 tier lower than the BERT model. But I would say it's already good enough for the bidirectional LSTM without like any fancy stuff like attention things like CNN to read the characters charts to get a representation of the world like ELMo. It actually did none of things like that, and still can have such performance, which is really impressive. So what are the implications? There's actually a few. Distill model is very good, just like I said. It's comparable to ELMo, and the shallow LSTM are more expressive than we previously thought. We just didn't really give it enough data to learn, and but still cannot beat its teacher. Yeah, it makes sense because students, you learn things from teacher, right? It's very hard to really surpass teacher. Okay, so here is the inference efficiency. So what they did was to compare the BERT large and the ELMo model and their bidirectional LSTM, distill bidirectional LSTM over their tasks. And the setup is they use NVIDIA V100 GPU, and the batch size was 521. And what I found was the speed of the bidirectional STM is actually 400 times faster than large BERT and 15 times faster than ELMo, which is incredible. But I would say for certain reasons, if you only use the batch size equals to 1, the difference between LSTM based model and the BERT based model will not be that significant, because when the batch size is big, LSTM recurrent neural networks can do batch, but when the batch size equals to 1, LSTM model couldn't do any batch processing, but BERT still can. As for why, you can look into the BERT paper and you will find out, and you can also do experiments by yourself. Okay, so the takeaways are bidirectional STM has very, very great representation power than we expected. And the task-specific distillation are fairly efficient because we don't need to let a teacher to teach students over a lot of corpus, over the whole Wikipedia. We don't have to. We just have to have a very small, specific annotated data, and we argument the data a little bit. Then we just let a teacher to teach student. It's quite fast, and we can have a really, really fast model, which is like 400 times faster than its teacher. It's really, really awesome. And you will have a less accuracy, less F1 score, but you can kind of have a really, really fast inference time. Depends on what you want. But I would say this kind of trade-off is quite worth it. So yes, this is all for today. A very interesting paper. And if you like it, don't forget to subscribe, because your subscription is my biggest support to make more videos like this. And you can also receive my videos in the first place. And that's all. Deep Learning Explainer. And have a nice weekend. And other than that, I will see you next time.